So we have an electron of mass ME that is located in a Coulomb potential, that's VR is equal to minus a squared over 4 pi epsilon naught r. So the proton is approximated as infinitely heavy, so that the reduced mass mu is just the mass of the electron. So in part A, we're supposed to determine the spatial region that is classically forbidden. And I just wanted to mention as well that the electron is in ground state, which is given in the problem. And we need to find the classically forbidden region of this electron. So in classical mechanics, classically, when we throw a ball at a wall, the ball is not going to be able to pass through the barrier. But in quantum mechanics, classically forbidden, so the electron can also exist in a forbidden regions, which means that the energy of the electron is less than the barrier. So that means the energy of the electron is smaller than the potential barrier. And since the energy is given in ground state, we already know this, that's E1 is equal to minus h bar squared over 2 me, and that's a naught squared. And that's just the Bohr radius, that's a constant, and it's given by 4 pi epsilon naught h bar squared over me e squared. And when we plug for a naught in this equation, we get for the energy, so we plug that in and we get minus h bar squared over 2 me a naught squared, that's minus h bar squared 2 me times 4 pi epsilon naught h bar squared me e squared, and the whole thing is squared. And so we can simplify a little bit here. We can take this away, so h bar squared is going to cancel this h bar squared, and another square is going to be left here, and that's simplified to, and we can take the e to the fourth power times me. We can take it in the numerator, and that's just going to give us e to the fourth power me over 2 times 4 pi epsilon naught squared times h bar squared. And so that's the energy, and that's supposed to be less than the potential energy, and that's just when we plug for the potential energy, we have minus e squared over 4 pi epsilon naught times r. And so when we plug those in, we get minus e to the fourth me over 2 times 4 pi epsilon naught squared h bar squared is less than, has to be less than 1 4 pi epsilon naught 1 over r. Oh, excuse me, it's supposed to be e squared over r. So we can simplify again here. We can simplify the e's, and one term is going to cancel the square over here, and so what we're left with is, and we can also multiply by -1, so we flip the signs because we don't want the minuses, and then we can just flip the inequality, so it's just going to be e squared me over 2 times 4 pi epsilon naught h squared is larger than 1 over r. So if we look at this, at the Bohr radius here, and if we compare it to the expression we have here, that's just the inverted Bohr radius, so that's just going to be 1 over a naught. So that's just going to give us 1 over 2 a naught is greater than 1 over r. And when we take the inverse again, the signs are going to flip again, so then we're going to get that r is greater than 2 a naught. So that's the forbidden area that we wanted to find. If the electron is greater than 2 times the Bohr radius, that is classically forbidden. And so now in part B, we're supposed to find the probability that the electron is located in this region. And we do that with the following formula. So we have probability is equal to the integral. That's a given formula of the radial probability. So that's just, we wanna take the integral from 2a naught to infinity, and since the electron is found in ground state, we're taking the radial in ground state squared. So that's just the radial probability of finding the particle in ground state, and that's also a given formula. That's 2 times z over a naught and to the power of 3/2 times e minus z r over a naught. And z is equal to 1 in this case because it's a hydrogen atom. So we have r10 is equal to 2 times 1 over a0, a naught, to the power of 3/2 times e to the minus r over a naught. And so when we square this, we're going to get a 4 here, and the 3/2 is going to cancel, so there's just going to be left like a to the power of 3, and we're going to get another 2 in the e function. So then plugging all this together, we're going to get probability is equal to the integral from 2a naught to infinity of 4 over a naught to the power of 3 times e to the negative 2r over a naught times r squared dr. And so let's just solve this integral. We can try to kind of simplify it. We can plug in a substitution when we use the lambda substitution of 2 over a naught. And so we can rewrite this whole expression as integral of 4 over a naught to the third e to the minus lambda r, because this whole thing is just becoming lambda, and then we have the r squared dr. And so with this substitution we can use a derivative rule, which allows us to take the derivative of the e function with respect to lambda, and that's just going to simplify the whole expression, because when we take the second derivative of this e to the power of minus lambda r, so if I take the derivative with respect to lambda, I'm just going to get from the first derivative is going to just give me minus r, and the second derivative is going to give me minus minus r times r, which is just r squared, and of course the e function itself. So when we compare this, we can see that this whole expression here is just equal to this, and so that's just going to give me 4 over a naught to the third, and I can pull that out of the integral because it's not a r dependent variable, so I can just pull it out of the integral, and then I'm going to be left with the second derivative with respect to lambda, and I can also pull that out of the integral because that's also not dependent of r, and then the integral itself from 2a naught to infinity of e to the minus lambda r dr. That's much more simpler to integrate as opposed to this expression, which we were supposed to use partial integration, I think, 2 times, and that's just going to be a little bit more complicated. And granted, taking the second derivative of the expression is also not going to be easy, but it's much more simpler in my opinion. So when we integrate this part, this integrated is going to give us just 1 minus 1 over lambda, and then the e expression. And then we have to evaluate this thing from 2a naught to infinity. So if I take the limit of the e expression to infinity, as when r goes to infinity, the exponential expression is going to go to 0, so that whole expression is going to be 0. And then I have minus 1 over lambda, and I can just plug 2a naught for r, and that's what we're left with, 2a naught. So minus minus cancels, so that's just going to become a plus. And then we can go back to the whole expression, which was 4 over a naught to the power of 3 times the second derivative with respect to lambda from 1 over lambda times e to the negative lambda times 2a naught. So then we have to take the second derivative of this whole expression, which involves the product rule, but in my opinion it's not that complicated. We can just do it really quickly. And so let me just first take the first derivative of this expression, which is So that's the first derivative, which involved the product rule. So we took the derivative of the first expression with respect to lambda, which is giving us minus 1 over lambda squared, and then the second derivative just multiplied, and then plus the derivative of the second expression with respect to lambda. So that's just going to give us a minus because there's a minus in the exponential. So we have minus 2 a naught over lambda times the exponential expression. So that's the first derivative, and now we have to take the derivative of that derivative, which involves like a double product rule, but it's also really easy to do. So now we take the second derivative of this whole expression, which is going to give us basically 4 terms because it involves a double product rule, and the minuses are going to disappear because basically every single minus is going to cancel each other out. So let me just speed up that process. So when we took the derivative of this expression, of this first expression, we got basically 2 over lambda cubed, which is the first expression derived times the second expression. I'm hoping you know how to take derivatives by now. And so then we took the derivative of the second expression, which gave us actually 2 a naught over lambda squared, and multiplied by the e expression plus 2 a naught over lambda squared times the e expression plus 2 a naught squared over lambda times e to the negative lambda a 2 a naught. So when we look at this expression, we can see that we have two similar terms. I'm hoping this is lambda squared. So this expression is the same as this expression, so we can sum them up. That's going to give us 4 a naught over lambda squared times the e function, and the rest is just going to stay the same. So then we have, I will just copy this on the next page. Actually, I'll just take the e expression in front of the brackets because it's all the same expression. So now we know that lambda is equal to 2 over a naught. Or we can resubstitute again to simplify further, and then we get 2 over 2 over a naught cubed plus 4 a naught over lambda, and the whole expression is, by the way, multiplied by 4 over a naught cubed. That's this one here. I just forgot to multiply together. So the whole expression is just multiplied with 4 over a naught cubed, and so I have 4 over a naught cubed, and here I have 4 a naught over 2 a naught squared plus so let's see how much we can simplify. We can cancel this 2 with one of these 2's here, so this is basically 2 cubed, which is 8, and then we're going to be left with a 4. This is going to just cancel, and this is 2 squared, which is 4 over 2. That's going to give us 2, and these a's will cancel, and 2 times 2 is 4. So we have 4 over a naught cubed, and we can take this a naught to the numerator because this is a double fraction, which is basically a naught cubed over 4 plus a naught, and this is a naught squared, and then we have one a naught here in the numerator, and that's just gonna give us a cubed, and the 2 is cancelled, the 4 cancelled, plus 2 a naught cubed again, and this is just e to the negative 4. So simplifying this expression here with the fractions, this is 3a naught cubed, this is 3a naught cubed, and this is a naught cubed over 4, so bringing it all together is going to give us, that's just a naught cubed plus, so we have to multiply the expression with 4 to bring it in the same denominator, so 4 times 3 is 12, 12a naught cubed over 4 times e, and that's just 4 over a naught cubed, so 1 plus 12 is 13, 13 fourths, a naught cubed e to the negative 4. And so we can cancel the a naughts, because in the end we also just want to get a simple number which is not, which has no units anyway. So we can cancel the 4's, and we have in the end 13 e to the negative 4. And if we plug that into a calculator, it's going to give us approximately 0.238, which is approximately 23.8%. So as we can see, there's a non-zero probability chance that the electron is going to be found in the forbidden regions, which is greater than 2 times the Bohr radius. That was it. Thank you.